Hi guys, this is Mr. Rut. Let's do some more physics. So we are done the electricity unit, at least what we're able to do with it during COVID. So we're gonna move on to our last unit of the year. I know there's only a couple weeks left. Normally we wouldn't be doing new stuff at this point, but because we're not having exams, we're just gonna keep going up until June 23rd. Now this last unit is waves, and we're actually skip. There's a whole other unit that we're skipping, but waves is really important. Waves is a huge part of physics. So, light travels as a wave, radio, sound, uh, gamma rays, water, all kinds of things travel as waves. And if you can understand the science of waves, then that is absolutely huge. It has massive applications in all kinds of fields, whether you end up studying physics or not. If you're anything related to electricity or, um, you know, uh, engineering or any kind of science, like you're going to find quantities, you're going to find things that are related to waves. And so this is a really important thing to understand. And if you're taking grade 12 physics, then there's a big waves unit in grade 12, so it's important to get the basics. So I hope you'll join me for the last couple weeks of learning this year. And let's get to it. So I thought I would just start with this demo from PhET, as we've been using PhET a lot. You guys should be pretty used to it. Now, I'm just going to basically play around with this and talk through some of the basics of waves, some basic vocabulary terms, some basic understandings of how waves work. And I'm going to ask you to answer some questions related to um, the sort of explorations within this demo. So make sure you can be taking notes as we're going along, but actually what I'd really recommend you do is go to the demo yourself and just kind of do the same things that I'm doing as we're uh, playing around with it. Now I haven't even looked at this demo, so we're going to see what is available within this. So go ahead, look it up yourself, pause the video, go to the waves demo on PhET. It's pretty easy to find, and let's play around with it. Okay, so we have three options: water, sound, and light. We're gonna start with water, and we're gonna do sound also. We're not gonna do light because it's not a big part of the grade 11 curriculum. It's more of a grade 12 thing. But anyway, let's get started with water. So if I press this button here, we have a drop coming out, and it's making a wave pattern. And it keeps, you've seen this sort of thing before. You drop a stone in the pond, uh, and it looks like something like this. You can see the ripples, right? And so this is basically what this is showing. Now, we're looking at it from a top view. So we're seeing the waves from above. We're not actually seeing the water rising and falling from this view, but you can tell which parts of the water are supposed to be like the high parts and the low parts. Now, those are called the crests and the troughs. Those are the technical wave terms for the high parts and low parts. So the blue bands here, those are the high parts, and the black bands are the low parts. The blue parts are the crests, and the black parts are the troughs. Now, some interesting stuff that we can play around with are over here. If you see frequency and amplitude, so if I change the frequency, well, before I do it, just make a prediction. Don't even try it yourself. It's good to try to predict things before you even try them, and then you test your prediction and you see if you got it right. And then if you didn't get it right, then you modify your understanding in your brain of what those things do. But anyway, make a prediction, and then let me try it out. So frequency, I'm going to increase it. And what we're seeing is that the waves are smaller, for one thing. They look smaller, like they're thinner. Like the radial kind of bands of the wave are thinner. The water is dripping out of the tap more frequently. And it might look to you like the wave is traveling faster, but it's actually not. So that's kind of interesting. Let's trace that. So I'm going to trace my mouse across one of the crests. So watch this. We're going across the screen on the crest, and you can see how long it takes. Now, if I reduce the frequency pretty low, okay, so watch what happens. So the waves are like bigger, and it really looks like they're going a lot slower. But actually, look here, I'm tracing the crest again. It's actually going at the same speed. Now the water is obviously dripping less frequently. And the waves are much bigger, but they're actually still going at the same speed. And if I turn it all the way down, then it's a very wide wave. So the waves are coming out very infrequently. Okay, let me go back to a medium frequency, and I'm going to change the amplitude. Now, you might know what that means from math class. So in your head, make a prediction. What is it going to look like if I change the amplitude? So let me decrease it. So we have a pretty low amplitude now. So you can see how the colors are more like faded. Now what that means is the wave is actually just like a smaller wave. It's not, like surfers want a big wave with high amplitude, because high amplitude means it's physically large in the water. So surfer wants a big wave so they can actually surf. Maybe somebody who's just swimming in the ocean and is worried for their safety, they want a low amplitude wave because they don't want to be carried away somewhere. So this is good for a swimmer, especially not a very good swimmer. And if I turn the amplitude up again, all the way to max, say, we can see a really big contrast between the crests and the troughs. Good for surfers. Now, a couple other things we can see here. So, side view. Cool. So this is nice, actually. So you can actually see the physical shape of the wave. And we can try changing the frequency. So you can see how the waves are much closer together now. They're much more frequent, or we can make them really spaced out and less frequent. A gentler sort of a wave. That would be good for a swimmer. And we can also see the amplitude. So right now we have a high amplitude. If I turn it down, we have a very low amplitude. So it's barely even a wave. It's almost like just a gently rocking water. Nice for putting a baby to sleep, I guess. That's kind of morbid. All right. Now, I think there's a way of showing a graph. Oh, graph. Yeah, here we go. So show the graph. Now look at that. You can actually, this is a really nice way of understanding the math of it. So we've got this really shallow, low amplitude wave. I'm going to turn up the amplitude, and you can see how the graph gives us taller sine waves. If I change the frequency, you can see how the waves get closer together. I'm going to go back to top view. And watch how the crests of the graph are actually going along with the blue bands, right? Because the blue bands are the crests. And if I trace a trough, it's with that black band there. Okay. So is there anything else we can do here? There are some tools for doing some measurements here. This tape measure will actually, so it's kind of hard, but let me pause it. So if I pause it, we can actually measure the distance in between, say, from one crest to the next crest. Looks like it's about 1.6 centimeters. But if I change the frequency, that should change, right? So if let's say I lower the frequency, now we should be getting waves much less frequently, and we can actually measure how far apart the crests are. So let's say from about there to about there. I should make sure that I'm going in sort of at a right angle to the side of the wave. Anyway, 2.9 centimeters. Now that's called the wavelength. This is a key piece of terminology or vocabulary for waves. The distance between one crest and the next crest is the wavelength. It should also work for troughs. So if I measure the distance from one trough to the next trough, I'm actually getting a larger number. So I have some measurement error, but it's pretty close. Maybe I'll try this trough to the next trough. Yeah, not quite the same. I'm not doing it quite right, but it should be the same. Theoretically, it's identical. Now let me put this tape measure away, and we can also see something kind of interesting here. So what I'm going to do is I'm going to position these two sensors. One of them's on a crest and one of them's on a trough. And I'm going to press play and take a look at these alternating graphs. So you can see that one of them is measuring, so they're sort of out of phase with each other, which is another wave word for you to know, is that basically when one of these is at the crest, the other one's at the trough. So you can see I paused it there approximately at crest and trough. Here I paused it, and they're sort of both in between. They're actually both at something called a node. The node is a point that's like right in the center line in between a crest and a trough. So it's when the water is at its average level. So if there were no waves, the water would be here. But then even when there are waves, the water is sometimes at that level, and that's called a node. It goes up and down. It goes above its normal and it goes below its normal, but sometimes it's right at its normal, and that's a node. All right. And yeah, I think that's about it for water waves. Oh, there's one more thing. So if I click this button here, this is now going to be a single pulse instead of a continuous wave. So let me press play there. And you can see that one is going to be a single pulse. And you can see that on the graph. Now it's gone, the pulse has passed, so there's no more graph happening there. And we can try single pulse with different frequencies and amplitudes. So turn up the frequency. There's one single pulse, and you can see it. It's got its trough and its crest, and you can see on the graph that the trough came first and then the crest. That actually makes sense, because if you think about dropping a pebble into a pond, the first thing that's going to happen is it's going to lower the water level because it's actually pushing the water down. And then in order to make up for that lower water level, the next little bit of water will be higher than normal to sort of like fill in the gap. So it goes crest and then trough when you drop a pebble or a droplet. Okay, let's go back and let's look at sound waves. So start the demo up again and wait for it to load. Loading. Sound wave. Okay, so this demo looks actually almost identical to the previous one. There's a few other things we can do. Yeah, so it looks exactly the same. I wonder what the side view looks like. It looks the same. I guess that makes sense. So here's the thing, sound waves. Now, water waves are sort of two-dimensional. Like a water wave basically travels along the surface. It is, of course, obviously, it's actually three-dimensional, but what I mean is the way it travels is really only like forward and out to the side. It doesn't really travel up and down. Like it sort of goes up and down a bit, but it's not like it's traveling up into space or down into the core of the earth or something like that. But a sound wave is different. It actually travels three-dimensionally in the sense that when I am making sound, when I'm talking out of my mouth, the sound is traveling in a sphere around my head. So it's actually going in all three dimensions more than in sort of a different way than water waves are. So that's why when we look at the side view, it's actually exactly the same. So, but it's actually showing you different things. So this is showing you the waves going up and down when we're looking from the side, whereas when we are looking from the top, it's actually showing you the waves kind of going, forward and to the side from my mouth, even though it looks exactly the same. Now, what should we look at here? So, okay, so we have this option to play a tone. I'm going to show the graph. The graph is nice, yeah. We have this option to play a tone. So I'm going to do that. Okay, so you can hear that. Now, what I want you to think about is what's going to happen when I change the frequency or the amplitude of this wave? What's going to happen to the sound? Let me start with amplitude. So just make a prediction. What's going to happen when I change the amplitude of this wave and we listen to the sound? Nothing. That seems wrong. Something should happen. Okay, what's going on here? Oh, there we go. It doesn't seem to do much from about 1/4 up to max. But once I get down here, there, I think you can hear that. That's weird that it doesn't really make much of a difference up here. Anyway, so amplitude is volume. So and if you look at the graph, look at the graph here. So let me play the tone again. You can see the amplitude changing. When the amplitude gets down to nothing, you can't hear anything. So amplitude is volume. So what about frequency? Take a moment, make a prediction. What is going to happen when I change the frequency of this wave? So the frequency is the pitch of the sound. That's a musical term. If you've taken music lessons, you might know about pitch. But it's, how high or low it sounds. So a really low sound versus a really high sound have different frequencies. And if you see a really frequent wave, then it's going to be a higher sound. So look at the graph. You can see it's more frequent. Turn the frequency down. Lower sound, less frequent. Now let's take a look at particles, because this is really interesting. So the question is, well, let me just show this to you guys. So let me play this. I'm going to turn off the sound actually. Okay, this looks kind of chaotic. This might be hard to understand. Let me just make the frequency and amplitude about medium. So, okay, this doesn't really look so much like a wave as much as the previous simulation. Like when I turn on waves, now that looks like a really nice pretty wave. That does not. That looks like chaos. But there's this nice option where we can view both. And you can actually kind of see the particles are sort of following the wave pattern. So let me pause it. Pausing it might be a good way to see this. So I pause it. Now take a look at the crests of the wave. You can see how the particles are pretty much falling in the crest, right? Like a couple of them are in the trough, but most of them are in the crest. And I could make that even more obvious if I turned up the amplitude, I think. So let's turn up the amplitude and you should see it even more clearly. Wow, look at that. It's kind of crazy looking. So most of the particles are in the crests. Very few of them are in the troughs. So what is actually going on here? So let me put it on slow. So watch what's happening with the particles. And in fact, what you can do is trace an individual particle. Like that's why they made some of them red. So trace a red particle and you can kind of see what's happening. So they're having these collisions and the particle's sort of being pushed out by other particles and then it's kind of falling back. It's just kind of going in and out. So each individual particle is not actually traveling out along the crests of the wave. They're actually just kind of going back and forth. And the motion of the sound, the way that it starts in a single place and then goes outward and travels to new places, it's not actually any one single particle that's actually going on that journey. It's just it's the pattern of the collisions of the particles that actually forms this outward traveling wave, even though the particles themselves are mostly just staying in the same place. And it's the same thing that happens with water. So an individual drop of water in the ocean is not actually traveling along the surface of the water with the wave. It's actually just going up and down. And so it's kind of an illusion that the wave is moving. It's actually just water going up and down, but it looks like a wave is doing this, but it's actually not. So that's kind of crazy. Anyway, we can see what happens with this, with the particles as I change I already showed you turning up the amplitude. If I turn down the frequency, say, I've got it on slow right now. That's good, actually. It's easier to understand when it's on slow. So now look how wide the waves are. And you can see how there are just a few main bands of particles on the crests. If I turn up the frequency, up to max, now this is going to be, okay, so these bands are much smaller, much thinner. You can see several, probably 6 or 7 crests and troughs, and you can see the bands of particles. And you can kind of see how some of the particles are like jumping from one crest to the next. And yeah, it's just I mean, play around with it yourself. Try different things. You can try some of these measurement devices, um, and you can see different qualities and properties of the waves. But I think that's all I can really think of to show you guys, and that's it. So thank you very much for watching, and enjoy the simulation. Enjoy waves; they're pretty cool.